Welcome to the UGC lecture series. This is a E-Pathshala lecture series on PG courses and we are talking about computer science. This particular module is about the subject of machine learning and we are going to talk about the mathematical concepts of machine learning. Here an important concept of machine learning called information theory. So, these are the people who are responsible for this particular module and we will be talking about information theory. So, information theory is a very important concept as far as machine learning is concerned, because information theory is used in some way or the other to understand how much of information is gained or lost because of the machine learning process that we are doing. Basically, as we have already seen in the previous modules, machine learning is involved is concerned with learning a model and then testing the model on training data. Now, when we do the testing, how do we judge whether the learning has actually happened? And for this purpose, we use an important concept of information theory called entropy. We will be going into different aspects of this particular concept as we go along. In fact, information theory is also used as a basis for decision trees, where we decide on which attribute we need to use in the decision trees, and that we will be talking about as we go further on. Now, the learning objectives of this module, where we are talking about basic mathematical concepts, are to understand the principle and practice of information theory, to know about the interpretation of this information theory and probability in real life, and to acquire knowledge about information and entropy. So, information source, entropy, sequences and Markov source, important concept, are keywords that will be associated with this module. Now, the outline is we are going to talk about information theory, we are going to talk about stochastic sources, we are going to talk about information in entropy, we are going to talk about entropy for memory sources, we are going to talk about source coding theorem, and we are going to finally give a summary of what we studied in this module. Now, if you look at this, an important person concerned with information theory is none other than Shannon. So, when we talk about information theory, we cannot be without talking about Shannon, and these are some of the important quotes about Shannon. So, what is information? So, instead of talking about the meaning of information, Shannon showed that information itself is a measurable commodity. This is a very important concept. It started off with information theory for communication purposes, that is where it started off, the famous information theory. But as machine learning picked up, and in today's world, information theory is very important, because we are not talking any longer about vague meaning of information, but we are talking about it as a measurable commodity. Now, today Shannon's insights help shape virtually all systems that are there that store, process or transmit information in digital form, from compact disc to computers, from Fresnel machines to deep space probes. So, anywhere you have information that is stored, that is processed or transmitted, Shannon's information theory plays a very important part. As far as this particular module is concerned, we are talking about the concept of information theory from the viewpoint of processing information, because we are bothered about how much of information is actually gained. So, we are talking about information gain when a learning algorithm is applied. So, information theory, in that way, information theory has also filtrated fields outside communication. Initially, it started as a communication theory, but later on it has it has infiltrated fields such as linguistics, psychology, biology and even arts, and very importantly into topics of today called such as big data analytics. So, first let us talk about the fundamental entities associated with information theory. So, when you talk about information theory, this is the the old view of information theory, but still relevant today. We have a source, we have a source coder and we have a channel coder, and then you have a channel decoder, a source decoder and a sink and a receiver. To understand this, what you have is an information source. That information source is I will talk about H, R and C later. This information source is the source is first coded, and then the coded information, it could be in the form of compression, whatever the coding. So, some processing, and then it is sent through a channel. This channel is very important because channel introduces noise. So, that we will talk about, and there is a capacity associated with the channel. Then it goes through a channel. So, you have a channel coder. Then from the channel, so this is as part this is part of the transmission system. Then you have the receiving system where the channel whatever is got from the channel is decoded, and then you have a source decoder, and finally a sink or a receiver. If you look at this definition of I mean, or the definition of information theory and the fundamental entities associated with it, you will see that it is a transmission system at the top and the receiver system at the bottom, where the transmission occurs through a channel. Now, let us look at what is this H, R and C. H is the information content of the source, what is actually the content, information content, and R is the rate of the source coder, what is the rate at which the transmission occurs. This is very important because we are talking about initially about transmission theory or communication theory, and C is the channel capacity. So, with these fundamental entities we will understand information theory. So, there are some fundamental theorems associated with this information theory. The first definition is, what is a channel? Now, a channel is anything transmitting or storing information like a radio link, a cable, a disc, a CD, it can even be a piece of paper. So, anything that transmits or stores information is called a channel. So, Shannon's first theorem says that error-free transmission is possible if R and H and C and R are there. So, if this is so, error-free transmission is possible. Shannon's theory 2 says that source coding and channel coding can be optimized independently. So, source coding, that is, remember the various steps, you have source coding and channel coding. So, those two aspects can be optimized independently, and binary symbols can be used as the intermediate format. So, this assumption, there is an assumption here that there is arbitrarily long delays. So, what we are trying to say is, if there is error-free transmission between RH and CR, then source coding and channel coding can be done optimized independently, which is a very important aspect of information theory, and you can use binary symbols as an intermediate representation. So, now let us look at, so as we saw before, we had an information source, we had a source coding, we had channel coding. So, here we are talking about that source. Now, information source we are assuming has some characteristics. So, there are some number of symbols n is the number of symbols, and the symbols itself are S1, S2 to Sn. Now, there is a probability of occurrence of each symbol. So, you have the probability occurrence of each symbol as P of S1, this is the probability of occurrence of the S1 symbol, probability P of S2, which is the probability of occurrence of the S2 symbol, and so on. There is a correlation between S1 and S2 or S2 and S3. So, then we have a concept called memoryless source. So, this is an assumption, that means we are assuming that each symbol is independent. What is the meaning of this? The symbol that is happening currently is independent of what happened before. This is called as memoryless source. And then you have what is called a message. Associated with the information source, you have what is called a message. A stream of symbols that go from the sender to the receiver is called as a message. So, it is a stream of symbols, sequence of symbols. So, with this fundamental notion we go along. Now, if you go here, you will see that we have defined something called a memoryless source. So, these are concepts that we will use to make some assumptions and make some modeling of the application we want. Next, we have what is called a stochastic source. Now, before we saw a memoryless source, now we have what is called a stochastic source. Now, the stochastic source, a source whose output symbols are x1, x2, 2 and so on. So, each symbol takes its value from an alphabet A. So, some alphabet, do not think it is only alphabet A, B, C, D, some alphabet, some set of symbols. So, it could be 1, 2, 3, it could be some hexadecimal, whatever. So, A is equal to A1, A2 to something. So, that is the set of alphabets from which a symbol takes its value, and then you have a model P of x1, x2 to xn, that is the output, assumed to be known for all the combinations that is possible. So, for example, a text is a sequence of symbol, each taking a value from the alphabet. So, the alphabet could be A to Z, capital A to Z, small a to Z, lowercase a to Z, and 1 to 9. It could also have exclamation and such special symbols. So, a text is a sequence of symbols. Here what we have tried to define is the alphabet. The alphabet in this case is as we have already discussed. And in this stochastic source, we have already defined there are what is a memoryless source. We have two types of sources. One is called a memoryless source and the other is called a Markov source. Now, this memoryless source, as we have already discussed previously, is a symbol which is independent of all the previous symbols. What this means to say is what will come here next is B. That B is independent of what happened before, whether A came or X came before. So, that means each symbol is independent of the previous one. So, what this means is the probability of this sequence, output sequence x1, x2 to xn, the probability is independent of each other. Now, next we have what is called a Markov source. This Markov source itself is again a assumption. What the assumption says is each symbol is dependent upon only the previous symbol, So, it is not memoryless. So, each symbol depends on the previous one. So, if you take the complete probability of the output sequence x1 to xn, it is dependent on the probability of x1, the probability of x2 depends on x1, the probability of x3 depends on x2 and so on. So, what it means is the probability of an output symbol xi depends only on the probability of the previous symbol, which is p of xi minus 1. So, that is what we have here. Now, we are going to discuss this Markov source a little bit more in detail. Now, we will assume we are in a state A, that is we are assuming that xk is equal to A. The probabilities of the next symbol are given. Now, we are assuming that there is a source here, alphabet, it is not source, sorry, alphabet A, and it consists of only 3 symbols, that is A, B, C. So, whatever sequence you have, it will consist of only symbols from this alphabet, so A, B or C. Now, let us look at this. What does this state diagram tell you? This state diagram tells you is that the probability of seeing B after seeing A is 0.7, the probability of seeing A after seeing A is 0.3, the probability of seeing C after seeing B is 1, the probability of seeing B after seeing C is 0.5, the probability of seeing C after seeing C is 0.3 and the probability of seeing A after seeing C is 0.2. I think you can understand what we mean by this. So, this Markov source is actually symbolized by this. So, what information it gives you is the probability of this occurrence of a symbol dependent on the previous symbol. Assume we are in a state A. So, let us assume that we are starting with A. So, the probabilities of the next symbols are A given A is 0.3, I have already explained this. The next symbol after A being B is 0.7, the symbol being C is not there, so it is equal to 0. So, given any state here means a symbol A, what is the probability of the other symbols in the alphabet coming is given as this. So, if you take here, now if you given B, what is the probability of A coming is equal to 0, given B, what is the probability of A? 0, given B, what is the probability of C coming? 1, given B, what is the probability of B coming is 0. So, here you are definite that after B what will come will be C only, because the probability is assumed to be 1. So, this is the Markov source. So, what the Markov source essentially says is that given if you are in a state, you can predict what will be the probability of the next symbol. The state itself is a symbol. If all the states can be reached, okay, the stationary probabilities for the states can be calculated from the given transition probabilities. The stationary probabilities for the probability of a particular symbol occurring. Markov models can be used to represent sources with dependencies that are one step back, because why? We are trying to find the Markov source defines the probability which is dependent only on the previous state. So, you can use a state diagram with several symbols in each state. So, stationary probabilities, what is the meaning of this? That is the probabilities of omega I given P of xk is equal to ai for any k when x minus 1, x minus 2, I minus k minus 2 are not given, can be determined. Now, let us look at analysis and synthesis. Now, what is a, so we looked at stochastic models and we had two type of stochastic models, memoryless source and Markov source. Now, stochastic models can be used for analyzing a source. The whole purpose here is we wanted to use this, right. So, find a model that represents the real world source and then analyze that model instead of analyzing the real world. So, and the same way stochastic models can be used for synthesizing a source. So, use a random number generator in each step of a Markov model to generate a sequence simulating the source. So, you can use it for both, for synthesizing the source as well as analyzing a source. Given a source, what will happen next? Given something, how will you get the source? So, both you can do. So, now we will come to the important part of information theory as far as machine learning is concerned. Here we want to measure the information contained in a message. So, how much information does a message carry from the sender to the receiver? For example, imagine a person sitting in a room and then he is looking out of the window. So, the person can see the sun is shining. Now, if at this moment she receives a call from a neighbor saying it is now daytime, does this message contain any information? Obviously, it does not contain any information because already she knows it is day because she has seen the sun shining. Another example, a person has bought a lottery ticket. A friend calls to tell her that she has won the first prize. Does this message contain any information? Yes, it contains information because before that phone call, before that message was received by her, she did not know that she has won the price. So, you can see the difference between the two. So, if you want to use a message effectively or if you want to use anything effectively, you should have information should be contained in the message that is transmitted. So, information and entropy. Now, assume a binary memoryless source like for example, a flip of a coin. Now, why do we call this binary? Because you can have only heads or tails. And why is it called memoryless? Because I get a head now, there is no chance, there is no particular probability that I will get a head or a tail next. So, how much information do we receive when the outcome is heads? So, I toss a coin, I get a head. Now, if it is a fair coin, that is P's heads is equal to P's tails is equal to 0.5, we say that the amount of information is 1 bit because we have got the information. If you already know that it will be heads, that is P of heads is equal to 1, the amount of information is actually 0. If the coin is not fair, that is P of heads is equal to 0.9, that is there is a chance that you will get 0.9. The amount of information is more than 0, but less than 1. The amount of information is the same if P of heads is equal to 0.9 or P of heads is equal to 0.1. Now, what are we trying to tell here? What we are trying to say is if you do not know the probability, that is if you say 0.5, then the amount of information you get because you got a head, someone tells you you have got a head is 1. If the probability of head is 0.9, it is not realistically possible, but if it is 0.9, then what the information you get is much less, or even if it is 0.1. But if you have an unfair thing, that is you have always it will be heads, you know that because it is not a fair coin, both sides you have head, then the information you get is 0. So, let us look at this part or in the same way that Shannon did. So, you assume a memoryless source with alphabet. Remember what are alphabet? The alphabets are all the possible symbols that can be there, A1 to AN, and symbol probabilities P1 to Pn. How much information do we get when finding out that the next symbol is AI? This is what is called as self information. According to Shannon, the self information of AI is called as I of AI equal to log of 1 by Pi. Remember, Pi is the probability of the symbol and AI is the self information of that particular symbol AI. So, assume two independent events A and B. Now, we are trying to explain how this came about. So, assume that you have two independent events A and B, events in the same way that we define events in probability, with probabilities of P of A is equal to probability A and P of B is some value P of B. For both the events to happen, the probability is P of A and P of B. However, the amount of information should be added and not multiplied. So, I of PA comma PB is equal to I of PA plus I of PB. So, I of A is equal to log of Pi. So, I of A is equal to minus log of Pa, that is equal to log of 1 by Pa. So, this is the way we get the information about a particular independent event. Remember, independent event. So, this is the way. Now, we want information to increase with decreasing probabilities. So, as the, if you have seen before, as the probability decreases, the probability of something occurring decreases. If you get the fact that it has happened, then the information that you get out of that is more. So, this is a very important concept, inversely proportional. So, as you increase the, the information that you get is more as the probability decreases. So, example 1, Pi is equal to 1. If you know that the information that you get, self information is 0. If it is 0.5, then it is 1. So, which logarithm, pick the one you feel like, you do not have to use any particular logarithmic base. If you pick natural log, you will measure in nats. If you pick 10 log, you will measure in Hartleys. If you pick the 2 log base 2, then you will get bits. So, normally they do log base 2. Now, we have found out the information of one symbol. If you average it out over all symbols, we get this, that is H is equal to 1 to n Piai. H of x is called the first order entropy of the source. Now, the source has n symbols. Okay. So, this can be regarded as a degree of uncertainty about what will come next. So, let us assume an example for entropy, which is called the binary memoryless source. So, let us assume that you have binary memoryless source 0 1 1 0 1 0 0 0 and so on. So, you have let P be equal to probability of xk equal to 1 and Q be equal to the probability of xk being 0, because it is binary, it can be only 1 or 0, or in other words that is equal to 1 minus P. Now, H is equal to P, you have only 2 alphabets 1 and 0, P log of 1 by P, and 1 minus P, this is we are applying this formula, but here we have only 2 bits, I mean 0 or 1. So, Pi is the probability of 1 and AI is the information content of 1 and so on. So, here you have P log of 1 by P plus 1 minus P, that is the probability of 0 log of 1 minus P. This is often denoted as HP. The uncertainty information is greatest when P is equal to Q is equal to half. So, this is the diagrammatic representation of the same. So, entropy itself has 3 properties. It can be shown that the entropy is H is equal to log n is reached when all symbols are equally probable or equiprobable. In our example, we have binary bits. So, it will be equally probable when 0 is the probability of 0 and the probability of 1 is equal to 0.5. The difference log n minus H is called the redundancy of the source. So, these are some of the properties of entropy, and it lies between 0 and log n. So, for a memory sources, so if you have memory sources, till now what we saw was for memoryless sources. Assume a block of source symbols x1 to xn and define the block entropy. So, you have here, instead of finding the entropy of one symbol, we want to find because at that point of time the symbols were independent, now it is dependent. So, it is 1 to n probability of this x1 to xn log of 1 by probability of x1 to xn. We are just extending the formula. Summation is over all possible combination of n symbols. Let the block length go towards infinity, divide by n to get the number of bits per symbol. The entropy for a memory source is defined as h of this n, limit of n going to infinity 1 by n h of x1 to xn. So, the entropy of a state Sk, now that was the entropy of the complete sequence. For one state you can define it as I is equal to 1 to r p of ki log of 1 by p of kl. Pkl is a transition probability from state k to state l, because the probability we have seen in the Markov source what is that state transition probability. So, averaging over all states, we get the entropy for the complete Markov source h of m is equal to k is equal to 1 to r p of sk h of sk. So, this p of sk is the transition probability from state 1 to the next state. So, if you talk about run length source, certain sources generate long runs or bursts of equal symbols. So, if you look here, this is you have A and B, and you have 1 minus epsilon from A to A, epsilon from A to B, and B to A is also epsilon, and 1 minus epsilon for B to B. Probably for a burst of length r into PR is equal to 1 minus epsilon r minus 1 into epsilon. So, the entropy is equal to minus of r is equal to 1 P of r log of r. The average run length is P, then you have this is a Markov source. So, we have come to the source coding theorem. The entropy is the smallest number of bits allowing error free representation of the source. Now, what we are trying to find here is what is the minimum number of bits we need to transmit information from the source to the receiver without error. Now, this is a very important concept in a number of applications of computing and communication, because we if you increase the number of bits, the price is more. So, we are trying to find out what is the minimum number of bits or the smallest number of bits we want to we need for error free transmission, and that is called as entropy. Now, let us look at what this means. Assume a long sequence from a binary memoryless source with P of 1 is equal to P. Among n bits, there will be approximately W equal to n P1s. Thus, M is equal to n over W, such is the typical sequences. Only these sequences are interesting. All other sequences will appear with smaller probability the larger is as n goes larger. So, how many are the typical sequences? So, M is equal to n by W, that is n factorial W factorial n minus W factorial, and this is approximately n factorial is approximately n to the power of n e to the power of n square root of 2 pi n bits per symbol. So, how many symbols you have, that many. So, if your enumeration needs log m bits, so 1 by n log m. So, 1 by n log of this particular factorial calculation will give you the number of bits you need for the transmission of typical sequences. So, example, consider the following sequence 1, 2, 1, 2, 4, 4, 1, 2 and so on. Obtaining the probability from the sequence, we are just counting this. There are 22 symbols and 22 is the length of the sequence, and 1 and 2 occur 4 times and 4 occurs 14 times. So, the entropy H is equal to 0.447, 0.447 plus 0.415, that is approximately 1.309 bits. This is how we will calculate. And if you have, there are 22 signals, we need 22 into 1.309, that is approximately 28.798, that is 29 bits to transmit. Now, check the symbols 12, 44, total symbols is 11. So, 12 appears 4 by 11 times and 44 appears 7 by 11. So, you have 0.945. So, you have 11 into 0.945, that is 11 bits to transmit the information. So, like this, if you can calculate it, here instead of taking it as 4 and 1, 2, we are taking it as 12 and 44, that is what we were talking about here. So, if you instead of transmitting as bit by bit, where you had 29 bits to transmit, you can transmit it as 12 and 44, in which case you need only 11 bits to transmit without losing any information or without error. So, let us look at the way Shannon did it, assuming a memoryless source, alphabet, symbol probabilities. This is how we assume, just look through at self information. So, similarly, I can calculate the self information for each and every. A1 is equal to 1 means how many, 2 means how many. For the same example that we had there, we can calculate the for 1, 2 and 4 separately, and this is what you will get. So, on an average over all the symbols, we have to calculate H is equal to, we have looked at this just the formula, this is just an example. X is called the first order entropy. So, for the symbols 12 and 44, the H order entropy is 0.94 bits. So, for 11 symbols it is 11 bits. So, this is what we have already seen. So, for binary memoryless source, we have already seen that it is half. So, this has 3 properties which you have seen. Now, using information theory, entropy measures the amount of uncertainty in a probability distribution, considering tossing a biased coin. If you toss the coin very often, the frequency of heads is say p, and hence the frequency of tail is 1 minus p. If it is a fair coin, you know it will be 0.5. Uncertainty in any actual outcome is given by entropy. Uncertainty is 0 if the probability of 1 or 0 is maximal, and if we have p is equal to 0.5. So, that is the time when we have uncertainty. So, P examples which are true and N examples which are false, our best estimate of true or false is given by this. This is an important aspect where we have positive negative you can look at. P is the number of positive samples and it is divided by P plus N, and P is the number of N is the number of negative symbols, and using the same concept that we use for 0 and 1 you can find the entropy. So, what we talked about here is we explain the model of communication, we outline the sources of information, we explain entropy, we discuss source and Markov source, and we describe typical sequences, and we decided in this whole module what we spoke about is how do we calculate the information content in a necessary to transmit information without losing anything, that is with error free. So, information theory tells us the information content of something, and this is important in machine learning for two reasons. One is to decide on how much of information is there in a particular representation, so that I can use that representation for my learning purposes. So, this is the main aspect that information theory comes, and in many of the research problems of machine learning, entropy is used as a measure of how much learning has occurred. So, thank you.